It's my first time to come to Vietnam. I'm very excited and honored. There are so many young faces. My topic is Accelerator Framework, UADK. I worked for Linaro for over 10 years and have been collaborating with HiSilicon for over 10 years. Now I'm maintaining the kernel submodule UACCE and also maintaining areas of UADK like the OpenSSL and DBDK. We are also upstreaming the SBDK UADK component. Here is the agenda. First, the overview and some components of the UADK, and lastly, the performance. As we know, there are many accelerators like GPU, NPU, TPU, and also more and more user drivers like DBDK, SBDK. Also, we want to the better performance like zero copy. We cannot want to memory copy from user space to kernel space. So it's better to directly have provided the user driver. And lastly, the security. We all know the kernel is safe. We can trust the kernel. But if the driver is in user space, can we trust it? This is our UADK overview. UADK is based on the IOMMU. So it provides boundary check and the permission check. For example, if your driver cannot access other area of the accelerator, you can only touch your own accelerator. So it is much safer. And our IOMMU provides SVA feature. That means shared virtual address. So in the user space, we can directly use the virtual address. And for it is a user space driver. In the user space, we can directly do the DMA to the accelerator. What's more, with SVA feature, we all know usually we have to use physical address, but with SVA feature, we can use virtual address directly. So it is very convenient. Thanks for the pass ID. We can do using multi-process because the pass ID can distinguish them. Then it contains several modules, the kernel module and the user space module. This is a general framework. In the bottom is accelerator. It can provide several queues. Each queue can provide a service, so many queues can work simultaneously. Now, how user space use that queue? So the accelerator have to register to the UACCE. With the help of UACCE, then the application, multi-application, can directly open the UACCE to get the access of the queue. For example, the left is pass ID 1, is application 1. The right is pass ID 2, is application 2. So they can run in the meantime. The pass ID can distinguish them. Also, in the pass application 1, we want to access 2 queues or many queues for the multi-thread for the better performance. So you can open multi times. The UACCE can use our IOMMU for the bind. So our IOMMU can bind the device to the current MM. The code is already merged in the kernel, in the 5.7. Is there here any question about this picture? This is a general framework of the UACCE. Okay, next. This is SVA, general SVA. We all know the MMU. CPU has MMU. It has a patch table. So the application uses virtual address. Also, device also has MMU. It's called SMMU or IOMMU. It also has a patch table. So there are 2 patch tables. If so, why not the same? So now the SVA feature use the same page table. The MMU and SMU, they share the one page table, only one page table, so they can know each other. With this, the DMA can directly use the virtual address. And also their page fault, our page fault, similar like the MMU. For example, in the SMU3, when their page fault happen, the handler to call the handle MMU fault. It is same as the MMU. Then it will provide the memory for you. Is that okay? This is how Accelerator use the USDE. In the Accelerator driver, in the pro process, it has to unlock USDE and then register to the USDE. The USDE was using the IOMMU feature to open the RPF feature and SVA feature. And after that, it will provide a chat device. So with that chat device, the user application can access to the Accelerator. In the remove, the USD will do the USD remove. Also, it provides some ops when the register, like get queue, put queue, start queue, stop queue, and memory up. Then, so after the registration, the application can directly open the USDE. It is a chat device, so you simply open the chat device. With that open, the USDE will bind the device, the Accelerator, with the current So after that bind, the virtual address can be directly recognized for the application and the Accelerator. And the USD will get a queue from the Accelerator. And after you open, after the application will map the MMRO is doorbell, just prepare DMA and send doorbell to tell the Accelerator to start the DMA. Also, map the other area for the DMA ranging. And then you can all control to start. After the preparation, you just prepare the DMA, prepare the data, and send a doorbell to tell the Accelerator to start. After that, you can just pull. You can pull the FFD, or just keep reading. And all the finished, you can put Q, and close FD for the last time. This is the user application to use USDE. That's the kernel module USDE. This is the whole picture of the UADK. The right is a picture. In the bottom is Accelerator. Then the kernel space, the kernel driver USDE. After then the user space, there is the library is the UADK library. We can provide the user driver. Currently we but be careful. There are two requirements. Firstly, the IOMMU have to provide the SVA feature. Also, the device have to support, because the pass ID we can use the Accelerator in the multi-process. So the device has to recognize the pass ID. If the Accelerator does not support SVA, you cannot use it. In the high silicon platform, currently we use crypto. Like crypto Accelerator can support this feature. We provide compression like zip, gzip, deflate, and ZSTD. Also, the asynchronous crypto, like ICDH, ECC. We know the async crypto is very costing. It needs a long time because it is not like the CMYK crypto. It's very simple and much faster. So I think like ICDH is very if you do it using the CPU, it needs a long time. So it's very suitable for the crypto, for the accelerator. We provide the IC, DH, and ECC. Also, the digest is just like a hash, MD5, SM3, etc. Now we support our UADK to the DBDK, also the SBDK. You can directly use it. Oh, sorry. This is the performance. The green line is using CPU. The brown color is hardware. We can simply see. For example, the first line SM4. If using the software and the hardware about 4 times better. Also, the CPU rate is much downgraded. ZLib and gzip also almost 20 times better. The IC is also 3 times better. This is performance data. we tested this on the high silicon Kunpeng 920 platform. This is a host. This is a guest. In the guest, there is we have to use virtual IOMMU. It needs the lasting translation. It is still in upstream. We use techniques to support the better performance in the guest. We know in the guest there is some penalty because there is a nasty translation from the virtual address in the guest have to translate to the physical address of the guest, and then lastly the physical address of the host. So there is some penalty. We just use some technique. Use a huge page. Use 2 megabytes huge page is used to decrease the TLB miss. With this technique, the performance in the guest almost comparable to the host, about 85% or 90% of the comparable to the host. This is the guest. This is the UADK test for the open SSL. The blue line is soft. The yellow line is using hardware accelerator UADK. You can see the sign, for example, the left sign is much better, 4 times. The verify is a little bit better. And SM3, for the big data, because hardware usually do better in the big data, big packet size. We have to prepare, and if using small size, the CPU is better because there is no preparation. SM4 is also the same. Using the big data is better. Here is DBDK. DBDK was also supported. It already merged in 22.11. We are now upstreaming for the SBDK. So in the SBDK and the DBDK, we can directly use the UADK components. We can see also the same. The small packet, the software is better because there is no preparation. You can use anytime with the CPU. But for the big packet, the bigger the better. Hardware is better. You just prepare data to the accelerator and then you don't care. Also, since the UADK provides the crypto and the compression, so now the UADK only have, if you use UADK, you have to have the accelerator. But sometimes you may not have the accelerator. So we are investigating using the CPU structure, CPU instruction. We tested this is tested with Neon CPU instruction. You can see the instruction is also better than the software. The software is not a CPU instruction, just a CPU. You can see it's also better. So the total solution of the UADK, we also added the CPU instruction, like the CE. We are CESV. CE means crypto extension. SME means scalable vector extension. They are ARM-V8 feature. So if you have ARM-V8 CPU, you can use these two CPU instructions. So we also adding these two instructions to our UADK solution. We are just adding this. See the blue line. Also, the OpenEULA ACC Lib, we have meetings bi-weekly. If you have interested, you can join this meeting. That is GitHub. This is the simple description of Ninaro. We come from Ninaro, and Ninaro has many maintainers. We have we always the top 3 contributor of Linux kernel since over 10 years, since 2011. So we have many. Also, we provide some like a special feature like TE security. TE is still developed and maintained by the Ninaro. So if you have interest, especially on the ARM ecosystem, you can contact with us. Yeah, that's all. Thank you.